Have you ever wondered what invisible forces the universe is hiding? What silent symphonies are echoing through space and time? Imagine a vast cosmic fabric, where every planet, star, and galaxy is a marble rolling on it. As these massive objects move, they create ripples that propagate through space at the speed of light. These ripples are gravitational waves, a concept once confined to Einstein's papers, now scientifically confirmed, ushering in a new era of cosmic exploration. In this video, we will unveil the mystery, delve into gravitational waves and the super-gravitational power shaping our universe, and explore cosmic events invisible to the naked eye, but which the universe's ears have listened to. Get ready for an adventure beyond what we've ever known. Welcome to SpaceTime's cosmic journey, where we explore the universe's deepest mysteries. In this video, we will delve into the Milky Way and its undiscovered secrets. Don't forget to subscribe to the channel so you don't miss other exciting space exploration videos. If you find this video interesting and helpful, please like and share to support us. In 1915, Albert Einstein published his general theory of relativity, a masterpiece that completely transformed how we perceive gravity. No longer a mysterious attractive force between objects, gravity was described by Einstein as the distortion of space-time, a four-dimensional fabric weaving our reality. Massive objects curve this fabric, and that's what we experience as gravity. This theory not only successfully explained phenomena that classical physics could not, such as the precession of Mercury's perihelion, but also made bold predictions about the existence of black holes and gravitational waves, concepts that, at the time, science hadn't even dared to contemplate.
When extremely massive objects accelerate, they create ripples in spacetime, propagating outwards like waves on water when you throw a stone. He called these gravitational waves. However, Einstein thought these waves were too weak to be detected with the technology of the time, and he was not wrong. For decades, gravitational waves remained a theoretical prediction, a whisper from the universe that no one could hear, hidden in the silence of endless space. It was more than a century later, on September 14, 2015, that humanity officially heard the universe's first symphony. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected a faint but unmistakable signal. It was the sound of two colossal black holes, billions of light-years away, colliding and merging, releasing an enormous amount of energy in the form of gravitational waves. This event, named GW150914, shook the entire scientific community, confirming one of Einstein's boldest predictions and opening an entirely new window to view the universe, not just through light, but through the very vibrations of spacetime. So what exactly are gravitational waves, and how do they affect us? Imagine space and time as a giant, smooth rubber sheet. When a massive object, like a star or black hole, moves or rotates, it distorts that sheet. This distortion doesn't stay put, but propagates outwards as waves, like when you shake a rug. As gravitational waves pass, they stretch and compress spacetime in directions perpendicular to their propagation. This effect is extremely tiny, so small that if a very strong gravitational wave passed through Earth, it would only change the size of an object by stretching and compressing it by less than 1/trillionth the size of an atom. This is why LIGO must use 4-kilometer-long interferometer arms and ultra-sensitive laser technology, carefully shielded from even the slightest vibrations on Earth, to detect changes smaller than 1/10,000th the diameter of an atomic nucleus. This is an extraordinary engineering feat.
What cosmic events can generate gravitational waves strong enough for us to detect beyond the sensitivity threshold of modern observatories? Primarily, the most violent collisions, the death dances of cosmic giants. The two main scenarios we have observed are the merger of two black holes and the merger of two neutron stars. The collapse of a supermassive star into a black hole or neutron star, supernova, is also predicted to be a source of gravitational waves, but has not yet been directly detected.
Black holes, these cosmic monsters with gravity so strong that nothing, not even light, can escape them, are perfect gravitational wave generators. According to general relativity, a black hole is a region of spacetime where the gravitational field is so intense that it creates an event horizon, a boundary beyond which there is no return. When two black holes orbit each other in a binary system, they gradually lose energy through the emission of gravitational waves. Their orbits spiral closer and closer, accelerating to near light speed before colliding and merging into a larger black hole. In the final moments before merging, they create extremely violent spacetime distortions. In just a fraction of a second, the energy released as gravitational waves can exceed the total energy of all observable stars in the entire universe combined. This is the clearest manifestation of the super-gravitational power we are talking about. Gravity at its most extreme, where spacetime is bent, twisted, and vibrates wildly to the limits of familiar physical laws. The merger of neutron stars is also an important and particularly interesting source of gravitational waves. Neutron stars are superdense remnants of a dead giant star, compressing matter to an incredible density. A teaspoon of neutron star material weighs as much as an earthly mountain. They have extremely strong magnetic fields and rotate very quickly. When two neutron stars in a binary system spiral into each other and collide, they not only generate powerful gravitational waves, but also emit a trail of electromagnetic radiation, light, X-rays, gamma rays, called a kilonova.
Event GW170817, detected by LIGO and Virgo in 2017, was the first time we observed both gravitational waves and light from the same event, ushering in the era of multi-messenger astronomy. This was a giant leap forward, allowing us to compare data from two different windows of the universe to gain a more comprehensive understanding of the nature of these violent cosmic events. In particular, kilonovae are believed to be the primary cosmic factories for creating elements heavier than iron, such as gold, platinum, and uranium. The detection of GW170817 provided direct evidence for this hypothesis, telling us that the precious jewelry we wear could have been forged in the catastrophic collision of two neutron stars billions of light years ago. Before gravitational waves, we were almost entirely dependent on light and other forms of electromagnetic radiation to observe the universe. But light has its own limitations. It is blocked by interstellar dust and gas, and it cannot escape from within the event horizons of black holes. Therefore, we cannot directly see the darkest regions of the universe, or the very early universe, when it was too dense for light to pass through. Gravitational waves are different. They pass through all matter without significant interaction, carrying direct information from the darkest regions of the universe where light cannot reach, providing unprecedented insights into extreme events and the early stages of the universe. Think of it as gaining a new sense to perceive the universe, a cosmic ear that can listen to the vibrating sounds of spacetime. If light shows us the image of the universe, gravitational waves let us hear its sound. We not only see galaxies and stars, but now we can listen to the magnificent collisions of black holes and neutron stars, events that shape the large-scale structure of the universe, revealing secrets that our vision could never reach. The detection of gravitational waves not only confirmed one of the most important predictions of the general theory of relativity, but also provided the first direct evidence for the existence of black holes at masses we had never measured before. It also allows us to test physical laws in the most extreme environments where gravity becomes the absolute dominant factor and matter is compressed to an unimaginable degree. This data not only helps us better understand the origin of heavy elements, but also paves the way for the search for new types of matter and interactions. The future of gravitational wave astronomy promises even more exciting and surprising discoveries. Next-generation observatories, both on Earth like third-generation LIGO, dubbed Cosmic Explorer or Einstein Telescope, with many times higher sensitivity, and in space, like the European Space Agency, ESA, and NASA's Laser Interferometer Space Antenna, LISA, will expand our observational capabilities to a new level. LISA, scheduled to launch in the mid-2030s, will be able to detect gravitational waves from supermassive black holes at the centers of galaxies, from intermediate mass black hole pairs, and possibly even from events occurring shortly after the Big Bang, providing deep insights into the universe's primordial moments when it was very young. We stand at the threshold of a scientific revolution. Gravitational waves are not just invisible ripples in spacetime, but messengers from the distant past, carrying stories of the birth and death of celestial bodies, of the extraordinary forces shaping the universe. They show us a universe far more vibrant, violent, and dynamic than light ever revealed. The super-gravitational power of black holes and neutron stars are not just destroyers, but also silent architects, creating cosmic symphonies that now, finally, we can listen to. This is a powerful testament to the universe's wonder and the infinite capacity of human intellect to decipher its deepest mysteries, step by step uncovering the true nature of spacetime and matter under the most extreme conditions. The discovery of gravitational waves has shown us an invisible, dramatic power at work in the universe. But behind these violent collisions, these symphonies of spacetime, is there an order, a harmony that governs it all? Are there physical laws acting as a compass for the universe, from tiny subatomic particles to colossal galactic structures? In our next video, we will explore these questions together. We will discover the harmony of the worlds, the physical laws governing the universe's operation, learning about the fundamental principles that have created the delicate balance, beauty, and even chaos in the universe we inhabit. Don't miss it.